energy doesn't flow where you think it does. When I was in my electrodynamics class, working through homework, I came across an equation that looked completely routine, just another formula in Griffiths. It was the Poynting vector. At first, I treated it like everything else in the chapter, but I paused and actually read what the equation was claiming, and I realized it was saying something that doesn't match how circuits are usually taught. According to Maxwell's equations, the energy in a circuit doesn't move inside the copper wire. The energy flows through the electromagnetic field in the space around the wire. But most introductory circuit courses still talk as if power is something that travels through metal conductors. So there's a disconnect between the field theory description and the usual circuit picture. In this video, I want to walk through what Maxwell's equations actually say, how Griffiths illustrates it, and why this way of thinking becomes important in real circuit design. Let's start with the simplest situation, a straight wire carrying a steady current. From Maxwell's equations, two fields exist around this wire. There's an electric field along the wire. It comes from a small distribution of surface charges that arrange themselves along the conductor to drive the current. And there's a magnetic field curling around the wire, produced by the current itself. Now, when an electric field and a magnetic field exist in the same region of space, there is an energy flow. The mathematical expression for that energy flow is the Poynting vector, S equals E cross B. If you actually work out the direction of this vector for a current-carrying wire, it doesn't point inside the metal. It points through the space just outside the wire, running parallel to it. So, in this field picture, energy leaves the source, travels through the electromagnetic field surrounding the conductors, and when it reaches a resistor, the Poynting vector points inward into the material, where the energy is converted into heat. So, in this simplest case, the energy is carried by the fields. The conductor shapes where those fields exist. At this point, a reasonable question comes up. If energy flows through fields in space, why do we need wires at all? Why doesn't energy just travel through the air from a battery to a light bulb? The reason is that the wire determines the geometry of the fields. Charges accumulate on the surface of the conductor. Those surface charges create the electric field that points along the wire. That electric field, together with the magnetic field from the current, sets up a very specific Poynting vector pattern that guides energy from source to load. If you remove the wire, those surface charges have nowhere to reside. The electric field pattern changes, and there's no longer a controlled path for energy delivery. The energy can still exist in fields in free space, but it spreads out rather than being guided efficiently to a particular device. So, the wire's role is to constrain and shape the electromagnetic field so that energy flows where we want it to go. Now, let's look again at the Poynting vector equation, S equals E cross B. This expression tells you two things. First, it tells you the amount of energy flowing per unit area. Second, it tells you the direction of that flow. The direction is set purely by geometry. The energy flows perpendicular to both the electric field and the magnetic field. Once you know that both E and B extend into the space around the conductor, it immediately follows that the energy flow must exist in that space as well. There is no way to confine the energy strictly inside the metal without violating the structure of Maxwell's equations. This is where the usual circuit language description becomes an approximation. At low frequencies, and for simple circuits, it's convenient to talk as if current carries power through wires. That picture works well enough for basic calculations, but it hides the underlying field behavior. In modern electronics, conductors are close together. PCB traces run side by side. Signals switch in a few nanoseconds. Fields expand and collapse rapidly. If energy is flowing in the fields around conductors, then nearby conductors will inevitably interact through those fields. Energy that is meant to flow along one trace can partially couple into another. This is what we call crosstalk. From the field perspective, crosstalk isn't mysterious. It's simply a consequence of overlapping electromagnetic fields and the corresponding Poynting vector paths. This is why high-speed circuit design focuses on things like controlled impedance, ground planes, and differential signaling. These are all techniques for shaping the electromagnetic field distribution so that energy flows where it's intended to and doesn't leak into neighboring structures. Once you adopt the field picture, these design rules stop being arbitrary. They become direct consequences of how Maxwell's equations guide energy flow. So, where does this leave the standard circuit picture that talks about voltage, current, and power in wires? It's not that the traditional picture is wrong. It's a reduced description that averages over the underlying field behavior. For many everyday situations, that approximation is good enough. But the field-based description is more fundamental. It explains not just where energy goes in ideal cases, but also why practical issues like crosstalk, radiation, and signal integrity arise. In other words, circuit theory is a useful abstraction built on top of electromagnetic field theory. When you need more precision, you go back to the fields. There's one last detail we haven't talked about yet. If energy is flowing through the electromagnetic field around the wire, how does it actually enter a component like a resistor? In the standard circuit picture, we say current flows through the resistor and power is dissipated. That's fine as a summary, but the field picture tells us how that transfer happens in space. Near the resistor, the electric field is no longer perfectly parallel to the wire. The material of the resistor allows an internal electric field to exist. That internal field interacts with the magnetic field produced by the current. When you compute the Poynting vector in this region, it points inward, from the surrounding space into the body of the resistor. So the energy does not travel through the copper wire into the resistor and then magically turn into heat. Instead, the energy flows through the space around the circuit, reaches the resistor's surface, and crosses into the material through the electromagnetic field. Once inside, that field does work on charge carriers in the resistive material. Their collisions with the lattice convert the energy into thermal motion. That's Joule heating, now described in field terms instead of just circuit terms. This also explains something subtle. If you replace the resistor with a perfect conductor, the internal electric field becomes zero, and the Poynting vector no longer points inward. No energy is absorbed, no heating occurs, exactly what we expect. By this point, something subtle has happened. At the beginning of this video, electricity in a wire probably meant what most of us picture instinctively: charges moving through metal, carrying energy along like water in a pipe. It's an image that feels obvious, almost unavoidable. It's the picture we're introduced to in basic physics. It works well enough to solve many problems, and because it works, we rarely question it. But Maxwell's equations never use that picture, not even once. They talk only about fields in space, electric fields, magnetic fields, and how those fields store and transport energy. The conductors we draw in circuit diagrams are not part of the equations themselves. They enter as boundary conditions that shape the fields. When you follow that logic all the way through, you end up with a very different intuition for what a circuit actually is.